Hi, my name is Parsali Mohammadi and I'm first year electrical electronics engineering student at BK University. I'm taking this video for EE102 Digital Logic Design course for section 1, in which we had to prepare a final project for our final. And in this video I'm going to present that project. In my project, I decided to work on a specific type of or packaging organization or sorting system, which is a SCARA robotic arm for RFID-based packaging system or sorting system, in which I designed a SCARA robotic arm for packaging sorting based on RFID. First, I'm going to explain a bit of the design of this robotic arm, and then I'm going to go to electronics and coding part of the design. For the design of this robotic arm, SCARA robotic arm, I started around a year ago. It's actually a previous project of mine, previous design of mine, in which a year ago I started by checking internet for different design, different structures, and by having some understanding of the design of the system, I started to design this kind of robotic arm. Firstly, I started from sketching of the robotic arm or the design in Fusion 360, and then it continues by working on the sketches and kind of upgrading them or changing them and even modifying them over time. For example, additionally, I changed some other parts in the design. In my first design, which I designed a year ago, I didn't include any type of switches or micro switches or any kind of sensors that could help the robotic arm to understand its relative location. In this specific one that I redesigned for EE102 course, I added a micro switch here for Z-axis, another one for motor 1, and another one for motor 2 or joint 2. Other than that, I started to redesign some parts, specifically changing some components like the base, which was something like this. This was prototyping part of the design, which had some problems with the placing of the motor and the shafts. After the understanding the problems, I changed the design and implemented in the main design. Additionally, I want to talk a bit more about the gripper of this SCARA robot that I designed. It wasn't exactly like this. I changed the design a bit from zero. Before this, I was using small M2 nuts, just mounting the screws for the system. But it had some small problems, like this kind of robotic arm, because of the stepper motor, has a vibration in the system. So I had to change the design that wouldn't make problem, because before this, vibration used to make screws, M2 screws in the gripper to open by themselves. For that case, I changed the design and started to add small heat inserts to gripper handle part, which I implemented like these, so that I could enter the screws and screw them here, and using the plastic structure of the 3D printed part, save the screws or lock the screws so they wouldn't open. And a small detail other than that, I changed everything, like this part too, or even the base of the Z-axis, in which I changed the ball bearing type, linear ball bearings, and structure of it a bit to kind of make it more stable. And other than that, the whole design was 3D printed by one of my 3D printers. And now we can go to the main part, which is electronics part. For the main part, or as a computer or the brain or the logic system of the SCARA robot, I use the basis tree, which functioned as the main part of the SCARA robot, taking the signals from switches or even Arduino just to understand its relative location or understanding the entry values. Other than that, for the functionality of the system, I built few shields so that could make my job easier for the system. Such that this one was a stepper driver shield, which is being used for A4988 series stepper drivers, in which I just connected the whole power connections and outputs easily, and using some header pins for outputs or inputs, as you see. But other than that, the main part of the design was the functionality of the design. For example, let's say one of the stepper drivers died or burned or get damaged. You could just get it and replace it easily. Other than that, there were other parts of the design for this small shield, in which I used jumper pins. Such that, for example, one of the jumpers is enabling the stepper driver to work. This one is for enable, and enable. But we have another jumper, as you see. Second jumper is being used to change the micro stepping settings of the stepper driver of the system, such that when I am trying to change the micro stepping of the system, I just need to remove these jumpers. But when we are talking about micro stepping, I'm talking about the revolution of the stepper driver. Normally, stepper drivers they have one turn for each 200 steps. Normally, I've designed this stepper driver shield to give voltage to the system in such a way that it's going to operate in quarter micro stepping, which means that it needs 800 steps for each revolution. When we are talking that 800 compared to 200 for each revolution, we are actually talking about the fact that we are increasing the precision of the system, since it needs more stepping for each revolution. For that reason, as you see, for this one, which is for Z-axis, I'm only using, I've detached or removed the jumper. And by doing this, actually, I'm setting this for 1/4 or quarter. This one is for Z-axis, since we don't really need that much of accuracy in the system. But in two of the stepper drivers, the jumper is attached. It means that it's changed or sets the stepping setting, micro stepping of the setting, to 1/8, which means that it needs 1600 steps for each revolution, and it increases the accuracy of the system. Other than that, we have jumpers colored codes. Blue means low voltage and red means high voltage or external entry. The main reason that I decided to use 1/8 micro stepping for the motor 1 and motor 2 is because of the problem associated with this kind of robotic arms. These robotic arms are known as SCARA, and they are, as you see, they are built by using belts and some pulleys with specific teeth number. And this causes some problems. In SCARA robots, we have a really interesting problem, which is known as coupling effect. And it is caused by these belts in such a way that when I stop other motor from rotating and only rotate joint 1, joint 2 also starts to move, and it's not stable in its system. That's why I'm using 1/8 stepping for higher accuracy. But in detail, I'm going to explain in the coding part. This one was the second shield or PCB that I built. This one was using a logic level shifter or converter, and we had some pull down resistors embedded. So what was the main reason for using a logic level shifter? If you ask, is that because of the wire lengths? As you see, my wire lengths are pretty lengthy, and because of this, servo motors can really receive the voltage, signal voltage, because of the voltage drop, because of the long length of the wires. So I was using the logic level converter just to change the voltage level of the servo motor signal pin to 5 volt from 3.3 volt and to a stable current level, which basis couldn't support it. Additionally, as I said, I use pull down resistors. When I was testing the system for the first time, I realized that when I trigger sensors, micro switches in the robotic car, they weren't triggering, and the stepper motors weren't stopping their movement. After some researching, I realized that basis is using embedded pull-down resistors for its own switches on the circuit. And because of that, I started to use pull-down resistors for my own micro switches for a clear logic level. Other than that, we go to the identification part. In identification part, I use the Arduino Duo and RC522 high frequency RFID reader, which is normally 13.56 megahertz frequency. The main reason that I use Arduino Duo was because of its logic level. It is ARM based and it uses 3.3 logic level voltage, in which I don't need any other logic level converter to change the voltage level from 5 volt to 3.3 volt, which was really suitable for the basis tree. Other than that, I was getting output of 4 outputs for 4 RFID cards for each packaging, for 4 packaging, in which each output was giving logic level of 1 or 0 according to the reading of each RFID tag, and we had a shared ground for the basis. And now we can go for the packages. I designed a small package-like thing just to resemble that, to show that how is it working. To RFID system, to identify each package system, I embedded the small RFID tags under these packages, so our RFID system could understand and comprehend which package is being used. Same goes for other one, and I've just showed the identification on them by using 3D printer. Other than that, this was the whole design part and electronics part, and small details. I built my own wires just using a creeper for better communication. I use some silicon wires for better. I just chop them according to the size and the connection port. As you see, they are all handmade. After this, we are going to video part the functionality of the part of the project, how robotic arm works and functions according to each packages. It's going to take around 4 minutes and 30 seconds. After that, after the video, I'm going to talk about debugging systems and some small implementation I did, and I wasn't able to talk in the class about that, which is really important and really interesting about the system. So yeah, and also at the very end, I'm going to put the 3D design formats that I did and pictures actually in the Fusion. Okay. Now we are going to the second part of it, which is related to code and homing system. Homing system was one of the important part of it because I did it in the first demo of the project. It took a bit understanding of the system because I was kind of implementing the same method or the same way a CNC or 3D printer works. So the whole thing started with the homing, or the whole code started with the homing of the system. After that, after the homing, it started the main code, or the whole part of the code, in which I decided to work on a really specific type of code, which was modular, in which we had a top module of the code, which was following and controlling some modules of the code. We had the top module, which was the controlling system of the code. We had second or sub module of the system, which was homing control. We had third one, again a sub module, which was kinematic, which was responsible for trajectory of the system. As you know, it's not really a simple thing to use this kind of stuff, and there should be a kinematics equation for this kind of robotic arm to make it move and do a specific type of operations. And at the end, we had a simpler kind of code or module, which was servo controller. Let's start with kinematics part. As I said before, there were some problems associated, like coupling of the system. For the coupling system, there were some calculations, or I could just measure the amount of the coupling in the system. I did both and implemented it in kinematic part of the code. And then it was the second part, which was really important part of the kinematics, in which, as I said, stepper motors are kind of working in stepping systems. So the important part was I'm using small pulleys with 16 T's, let's say, in stepper motors, and they had to know, the system should know, how many rotation or how many steps it should move each motor to have a specific type of rotation. This was all happening in the kinematics module, and it was controlled by specific libraries like IEEE math or numerical. IEEE numerical, mainly that. Other than that, I want to talk about how do I give the coordination of the system. I kind of build a specific G-code system for my own robotic arm, for SCARA robotic arms. I built the first module, programmable, or not programmable, let's say easier, changeable, in such way that we had three values. First value was corresponding to the z-axis. It was in millimeters. For example, this one is 150 millimeters. It was taking the z-axis 150 millimeter up from the origin. Second one was in the second location we had for the motor 1, but this one was in degrees, and it had a maximum degree range of 280 degrees. And the third location is same as first motor, it is in degrees. Then we go for the location of the system. I kind of follow the same structure of the 3D printers, how they home or understand their relative location, or they go to a specific location. My system had 6 predefined locations. Position 1, which was known as common position 1 in the programming or VHDL code, which was the RFID reading part. It was going to go and take the packages when receiving signal from RFID reader. So it was the location of the RFID reader. Second location was buffer location of the SCARA robot. Buffer locations are one of those typical things that normally being used in 3D printers or CNCs. They normally use such things just to stabilize the mechanical movement, or just for safety reasons. It depends. So these were common locations or common positions of the system. Other than that, we had 4 other positions, which were special position or specified positions for each RFID tag associated with these tags, in which when each of them were triggered, automatically top module was taking them to kinematics part and using them as giving order to stepper motors of the system for understanding the specific location of the system. Other than that, I tried to design the whole thing specifically for debugging or being easy to repair, as you saw from the small PCBs I built, shields. And the Arduino itself had one of these things, and it was actually helpful in my project. In my Arduino, I use serial output of the Arduino, or the serial monitor normally known. I was reading the serial monitor by using my laptop just to understand that if my Arduino can understand each RFID tag or identify them or not, which helped me because RFID tag corresponding to the D wasn't working probably, and it helped me to identify it because it was showing unknown RFID tag. This one was for debugging and kinda solving a problem. The same goes for bases too. As you know, on the bases there are small tiny LEDs, SMD LEDs used there. I use them. I used just 4 of them and ordered them in a specific pattern for a specific type of situation showing. First one was with the most significant digit. I used 4 bits, 4 LEDs. The most significant one was 0. It was always off. This one was showing the homing state of the system, in which the most significant was always 0 and off. And by doing this, I was able to understand that does the system work or not. For example, let's say the problem is from the bases or my motors, such that when state was going to 1, 0, or let's say from starting 1, least significant, I understand that it's initializing. But this happens when I turn on the system, so it wasn't able to show it in the video. Second statement or state was 10, 1, 0. Motor 1 homing. Then after that, after motor 1 homed, it goes to motor 2, which is 11, which says that motor 2 is homing. After that, it goes 100, which means that the axis is homing. And at the end, it goes to 0, 1, 0, 1. The axis moving up, which is the identified homing position of the system. After that, it was time for operation of the system, in which the most significant bit was 1. In the system, when it is 1, 0, 0, 0, it means that system is idle. Everything is done, homing is done, and there is no input. We go to 1, 0, 0, 1, which means that operating at common position 1. It's going to common position 1 to take the package. Then it was going to 1 0 1 0, which means that it is operating at position 2, going to position 2, or getting ready for that. Then it goes to 1 0 1 1, which is the operating at the locations of stated for each RFID tag. And then after finishing this, it goes to the position 1 1 0 0, which says that it is returning to the homing position. And after this, I added a small thing related to coupling of the system, which was rehoming of the system. Rehoming helped my system to gain its proper position again, because there were some errors in the system and it wasn't really going to the homing position. That's why I did something like that for only motor 1 and motor 2. And then, as I explained this, for lowering errors, it was going to the LED structure of, or LED state of 1 1 1 0, which was for the repositioning of the motor 1 and motor 2. And at the end, we have really weird thing for, this is special for debugging, the position of 1 1 1 1. This is for unexpected state. If something happened, a sensor doesn't work properly, this is specifically for this. Everything finished about explaining the code, how does it work, and also a small thing that I didn't mention. Servo module had a specific working format. My servo motors weren't working properly. I was giving 2 millisecond signal output with 50 megahertz for the system, but it wasn't really functioning real close in it. So I checked it with oscilloscope 2, and I realized that there were some problems in this servo motors. So I really tested and realized that I have to give a signal around 3 milliseconds, so they could close around 100 degrees, which kind of solved the problem. Other than that, another thing that I didn't mention was the frequency. For the homing, I'm using 1 kilohertz, which is lower frequency. And for the normal moving, I'm using 2 kilohertz, which is normal step of the speed of the system, which you'll see. After this, we are going to watch the video of the homing of the system and how the LEDs are going to work according to each situation, as I mentioned. And at the end, as I said, I'm going to put the pictures of the design in Fusion 360.